Welcome back everyone. In this lecture I will continue with the properties of cyclic groups. So first let's recall what we have done so far. So we proved a very important classification theorem of cyclic groups. So if G is cyclic, so depending upon the order of G, then we proved that either G is isomorphic to the group of integers or G is isomorphic to Z modulo NZ. Okay. So, this is the first result that we proved, and the second result, if G is isomorphic to Z or order of G is infinite, so then there is a one-to-one correspondence between the subgroups of G and the natural numbers, non-negative integers. Okay. And we also proved that if G has order finite and it is exactly capital N, then the subgroups of G has one-to-one correspondence with those devices of N. Okay. So, this is something we already proved. So, now we will actually ask a very fundamental question, that if you fix a cyclic group, then how many generators are there? Okay. For example, let us start with integers. So, then we already seen that if this integers is generated by some n, then if and only if this n must be plus or minus 1. So, the similar thing must be happening even for infinite cyclic group. Okay. If G is infinite cyclic group, so and G is generated by x, so then you can prove that, so G is generated by some x power a if and only if a is plus or minus 1. So, this is something I will leave it as exercise, because this is something we have proved already for integers. So, now what will happen to finite cyclic group? Okay. Let us start with finite cyclic group. Okay. So, let us take G, which is cyclic, and order of G is capital N, which is finite. So, then it makes sense to actually count the number of generators of G, because G itself is finite. So, the number of generators also must be finite. Okay. And that is well defined number for given G. So, let us call it, that is N of G. Okay. This is the number of generators of G. Okay. So, since once you fix the order and all cyclic groups of order n, they are all isomorphic, then under isomorphism it is easy to see that generator must be mapped to generator. So, that I will leave it as exercise. If you have an isomorphism between G and G dash, and if x is generator of G, okay, and G generated by x, so then you can prove that G dash is also generated by the image of x. Okay. And vice versa, you can also start with the generator of G dash, and then you can actually get phi inverse of that element, and that will generate G. So, in particularly there is a one-to-one correspondence between the generators of G and generators of G dash. Okay. So, this is another exercise. So, there is one-to-one correspondence between the generators of G and G dash. Okay. So, this is 1, this is maybe 2. So, now because of this, since there is a unique group Z mod NZ up to isomorphism. Okay. So, this problem is actually exactly counting the number of generators of Z modulo NZ. So, let us see what happens to that. So, if you take G to be NZ, okay. So, what we proved so far, let us recall, if G is generated by x and order of x equal to n, then we also proved that order of x power a is nothing but order of x divided by GCD of order of x comma a. Okay. So, in particularly x power a generates G if and only if order of x power a must be equal to order of x. Okay. But that is if and only if GCD of order of x comma a must be 1. Okay. So, any element of G must be power of x. So, then this last characterization actually kind of gives you how to get all possible generators of G. So, the generators of G is indeed G is those powers of x such that, so you can take a to be between 1 to n minus 1 and GCD of order of x comma a is 1. Okay. But easily you can see that this has 1 to 1 correspondence between those integers from 1 to n minus 1 such that GCD of order of x comma a is 1. So, the number of such things is given by this Euler phi function. So, this is exactly phi of n. Okay. So, Euler phi function basically counts such numbers. So, those a such that a is between 1 to n minus 1 and GCD of a comma n is 1. Okay. So, now this actually kind of motivates us for the following important question, like how do you compute this phi of n? Okay. So, phi of n actually gives you the number of generators of G, that is fine, or number of the generators in Z modulo n Z, but is there any way to compute this phi of n? So, it is easy to see that what will be phi of 1. So, phi of 1 by definition it is just 1. Okay. So, because there is exactly one generator. So, maybe you can allow here maybe n, so that there will not be an issue. Okay. If n is greater than 1, you can take it to be n minus 1, but when to include 1, you can take it to be it is between 1 and n. So, now what will be phi of 2? So, phi of 2, if you think about it, so how many numbers are there like between 1 and 2 which is relatively prime to 2 is just 1. So, what is phi of 3? Phi of 3 is just 1, 2, 3. So, 3 is not relatively prime and 1 and 2 are relatively prime. So, it is just 2. Okay. So, phi of 4, you can see that it is 1, 2, 3, 4. So, 2 is not there, 4 is not there, it is again 2. Phi of 5 is 1, 2, 3, 4, 5, all are relatively prime, okay, except 5. So, it is 4. So, it is easy to see that phi of any prime p must be p minus 1 for prime p, okay, because all the numbers that are below p 1 to p minus 1 they are relatively prime with p. So, what happens to, for example, phi of p square? Okay. So, you are trying to count those integers from 1 to p square which are relatively prime to p. So, if you think about it, if d and p square they are not relatively prime, then p must divide d. Okay. If d and p square, the GCD of this is greater than 1 if and only if p must divide d, because the only divisors of p square are 1, p and p square. Okay. And if you take d from less than p square minus 1, so then this is what happens. Okay. So, then how do you count this? So, here is the way to count. So, for example, you can list them 1, 2 etc. p, and then p plus 1, p plus 2 etc. p plus 2p, okay, which is sorry, let's do it in some other way. So, I want to count it up to p square. So, we take it to be so here p minus 1 p, and then you add p minus 1 plus p, and then here 2p, and then if you keep doing this, so you will get here p square, and then here p square minus 1, okay, and then here you get p minus 1 times p plus 1. So, you can list all the numbers like this, and then you can see that the only numbers that will have some p as divisor is these numbers, the last column numbers p, 2p, 3p, all of them must be having p as divisor. So, that means you can take all these numbers, okay, they are all relatively prime with p square. So, how many numbers are there? So, each row has p minus 1, and then how many columns are there? You can see that it is exactly starting with 0, and then you are going up to p power p minus 1 plus p minus 1 plus 1, okay, because this is the one you are going. So, this is 0 times p, and then 1 times p equal to p, and this is the thing you are going. So, basically it is exactly p minus 1 plus 1, this is the number of rows, okay, and the number of columns exactly only in the red, okay, that is p minus 1. So, the total number is exactly p minus 1 times p, which is p into p minus 1. So, basically this cardinality of phi of p square is p into p minus 1. In other way, it is p square minus p. So, you have totally p square number of elements, and then you have to delete those integers which are multiple of p. Those integers which are multiple of p exactly lies in the last column. So, that is you can say. Now, if you generalize this proof, you can easily prove that phi of p power any r is nothing but p power r minus p power r minus 1. Okay. So, you can see that 1 to p power r, there are p power r numbers, and you have to actually delete those numbers which are multiple of p. Okay. Then you can easily see that there are p power r minus 1 numbers which are multiple of p, namely p, 2p, 3p and so on up to p power r minus 1 times p. Okay. These are all the numbers that you are supposed to delete. Okay. So, that means you have exactly p power r minus p power r minus 1 numbers which are relatively prime to p power r. So, now if you are interested in computing other numbers which are, let us say, composite numbers. So, what one can do? So, one can use this formula. So, phi of mn will be exactly equal to phi of m times phi of n whenever the GCD of mn is 1. So, there are many ways actually one can prove this. Let us give group theory proof. Okay. So, we know that given any cyclic group of order n, the number of generators in that group is exactly phi n. Okay. So, in particularly if I take a subgroup, okay, of order d, if you take H is subgroup of G and order of H is D, so then you can see that the number of generators of H, okay. So, those are all, so because there exists unique subgroup of order D, so any element of order D must lie inside this subgroup, okay. And so, the number of elements of G of order D will become exactly the number of generators of H, okay, because there exists unique subgroup of order D, that is something we have already proved. So, now this is somewhat helps us to actually understand what will happen to this phi of Mn. Okay. So, phi of Mn definitely count the number of generators of the group that has order Mn. So, start with the group which has order Mn. Okay. For example, Z modulo Mn Z, you can take this. So, this is as your example. So, this is your G. So, now what happens, the number of generators of G is equal to phi of Mn, okay, that is very clear. So, now what we are going to do, we are actually going to say that these generators can be obtained in some specific way, so that this number exactly becomes equal to the product of this phi of M and phi of N. So, let us see what we can do. Okay, start with the generator, call it X. Okay. So, now since this Mn they are relatively prime, so then you have some A and then B such that A M plus Bn is identity, where A B are integers such that this happens, because M and N are relatively prime. Okay. In particularly what we can do, we can see that this X is nothing but x power M times A times x power N times B. So, you can write it this way. Okay. So, now you can call this is Y and then you can call this is Z. So, we claim that the order of Y must be N and then order of Z must be 1. So, what is our claim? The claim is order of Y must be N and order of Z must be M. So, basically what we have done, okay, if you think about it, so you have written X as some YZ, namely x power M A, Y power N B, okay, this is my Y, this is my Z, and we are claiming order of Y is N and order of X, order of Z is N. Yeah. Okay. So, let us verify this. Okay. So, Y order of Y is N. Okay. If you take Y power N, then this is exactly x power M power A power N. So, then you can see that this is x power M and A, which is identity, because order of x is M n. So, that will imply that order of Y divides N. Okay. So, now we want to say order of Y is equal to N. So, how to say this? Okay. So, now if you start with some other power, Y power k is identity, Y power k is identity, then that would imply that x power M A k is identity, and that would imply that M n divides M A k. Okay. But go back to your A. Your A is satisfying this A m plus B n equal to 1. So, that means A comma n is also the GCD is 1, because A is here, n is here. So, A and n are must be relatively prime. If there is a divisor of A and n, then that must to divide n, divide 1. So, that means the GCD of A and n must be 1. So, then what you can do, you can see that from this n divides A k and A and n are relatively prime. So, that will imply that n divides k. We already shown that order of Y divides n. If you take this k to be your order of Y, so then you have seen that n also divides k. So, that proves that k is equal to order of Y equal to n. So, similar argument shows that order of Z is also m. Okay. So, basically you have written this x as product of two elements y z such that this r of y is n and r of z is m, and we will claim that this is actually a unique expression. So, there are no, this is the only way you can actually split them into product of two elements. Okay. So, suppose if you have other splitting, so let us say x equal to y z and then y 1 z 1 such that order of y 1 is n and order of z 1 is m. So, then this should imply y equal to y 1 and z equal to z 1. So, this is our another claim. So, basically given x, we are saying that there exists unique tuple y comma z such that y x equal to y z and r of y equal to n and r of z is m. Okay, how to prove this? You can see that y z equal to y 1 z 1 implies y 1 inverse y 1 equal to z 1 inverse z 1, sorry z 1 inverse z. Okay, now you can see that order of this element actually must divide n, order of this element must divide m, but both m and n are lately prime. So, that means order of this element must divide, call this element some u. You can see that order of u must divide m and order of u must divide n, but both m and n are lately prime, that implies order of u divides 1, that implies u is identity. If u is identity, that would imply y 1 equal to y, okay, and z 1 equal to z. So, that proves the uniqueness. So, let us summarize what we proved. If G is generated by x, okay, then there exists unique tuple y z such that x equal to y z and order of y equal to n, order of z equal to m. So, this is what we prove. Okay. So, now any generator can be written as product of two elements and one has order n and one has order m. So, this is unique. So, that means if you are interested in counting such x, then it is enough to count the number of y's that has order n and number of z that has order m, okay, the product of them. So, why? Okay, so, let us see. So, the number of the set of generators of G is now has bijective correspondence are equal to, I can say y z, where y and z are coming from G such that order of y equal to n and order of z equal to m. So, the correspondence is given by x goes to y z. So, now given this tuple y z, it is easy to see that the order of y z must be mn. Okay, that is also something we have proved already, because they are lately prime mn. So, this is actually gives 1-to-1 correspondence. So, but how many elements are here? You already, if you go back to our observation, the number of elements of order d, okay, this is the observation that we already made. So, if you have a cyclic group, order of G equal to n, G is cyclic, number of elements of order d is exactly equal to phi of d, because it is exactly the number of generators of that unique subgroup of order d. Okay. So, in particularly for this y, you have exactly phi of m choice, phi of n choices. For this z, you have exactly phi of m choices. So, the cardinality of this equal to, so this cardinality is equal to phi of n times phi of n, but this cardinality is exactly phi of mn. So, both must be equal. Okay. So, if you want to actually tell you more into like in group theory language, basically what we proved isomorphism between two groups. Okay. One is z modulo m and z, another one is z modulo m z cross Z modulo NH. Okay. So, there is a natural isomorphism between these two groups, and as I said, the isomorphism always preserves the number of generators. So, the number of generators here is exactly phi of Mn, and the number of generators here is basically product of the number of generators. So, that is just phi of M times phi of N. So, this is what we indeed proved. Okay. But still I have not introduced what is direct product. So, we will actually introduce. So, basically this isomorphism tells you that phi of Mn is exactly equal to phi of N times phi of M. Okay. So, now we are indeed ready to actually state and prove our characterization of cyclic groups. So, recall, so far what we have done, okay, that is what gives us characterization. So, the following are equivalent. Let G be a group. Let us start with finite group, okay, and assume that R of G is capital N. So, then the following are equivalent. One is G being cyclic, and second is, so given for all D divides N, there exists unique subgroup of order D in G. The third thing is, for all D divides N, there are exactly phi of D elements of G of order D. Okay. The fourth thing is, for all D divides N, there exist at most phi of D elements of G of order D, and fifth one is, for all D divides N, there exist at most one subgroup of G of order D. Okay. So, I will actually prove 1, 2 and 5 are equivalent. I will leave other things are exercise. Okay. Basically, it uses the same arguments. Okay. So, note that if G is cyclic, we proved that there exists unique subgroup of order D in G for all divisor D in N. So, since any element of order D must lie in this subgroup, so and this subgroup must have exactly phi of D generators. So, there are exactly phi of D elements of G of order D. Okay. So, 2 implies 3 will be easy, and 3 implies 4 again is easy, because if there are exactly phi of D, then there are at most phi of D. So, now 4 implies 5 is also easy, because if there are at most phi of D elements, either the subgroup exists or do not exist. If it exists, then it has to be at most 1, because then that subgroup is again cyclic. Okay. Sorry, that subgroup can have I guess, yeah, it cannot have 2 subgroup of order D, maybe like 4 implies 3, you can take it as success. Okay, let us see, like before proving this, what information that we get about cyclic group, and then that is what used in the proof. So, if you start with G, which is cyclic group of order N, okay, which is isomorphic to this. So, then there are 2 ways to count the number of elements in G. Okay, the number of elements in G can be partitioned into the following sets, following disjoint sets D, that AD, where D divides N. We have already seen that if you take some element of G, okay, so that has to be of the form x power A, then the order of that x power A should be order of x divided by GCD of order of x comma A. So, in particularly order of that x power A divides R of x. Okay. So, that is why it will be inside one of this AD. What is AD? AD, those elements y in G such that order of y exactly equal to D. So, each element has some order and that order definitely divides n. So, that given any element should be in AD, and because the orders definitely partitions the elements, okay, one element cannot have two different order. So, this is a partition of your group G. Now, what this partition indeed says? So, it says on the right side you have the cardinality of G, on the left side you have the cardinality of AD, D divides n. But we have already seen what is the cardinality of AD. The number of elements that has order D is exactly phi of D. So, basically this says the summation phi of D, D divides n is exactly n. So, this is some number theory identity that we get it for free by understanding the number of generators in the cyclic group. So, the number of elements is exactly given by summation phi D, D divides n. So, this is what used in the proof also. So, let us go through the proof. As I promised, I will prove 1 implies 2, 2 implies 5. 1 implies 2 I already proved. Given any divisor D, there exists unique subgroup of order D. So, now 2 implies 5 is obvious. Okay. If there exists unique subgroup, then for given D there will be at most one subgroup, either group is there or not there. Now, you assume 5. So, only the non-trivial thing is 5 implies 1. 5 implies 1. So, G has the property that given any divisor D of n, there exists at most one subgroup of G of order D. Okay. So, this is what they. So, now we want to prove that G must be cyclic. To prove G cyclic, it is enough to prove A capital N is non-empty. Okay. This A capital N we have already seen, this is non-empty if and only if G is cyclic. So, we indeed prove this. Okay. This is our claim. We will prove that A is non-empty. So, this is what we prove. Okay. So, how do we prove this? So, look at G, and given any element it will have some order. Okay. So, definitely you can write G as union AD, D divides n. Okay. So, what is AD? Again recall, AD is those elements x in G, maybe I will call it again y, such that order of y is D. Okay. Okay. So, here yeah, maybe I am I still yeah. So, I do not need to use Lagrange theorem. I was wondering whether I will use Lagrange theorem. So, it is not needed. So, because the way it is given, G has the property that given any divisor there exists at most one subgroup of order D. Okay. So, now if I start with some element, okay, of order D, so then I guess it uses Lagrange's theorem. Okay. So, let me state the Lagrange's theorem here. Okay. It is one of the consequences of Lagrange's theorem. If G is some abstract group and X is an element of G, okay, and the order of X is finite, and again you assume that order of G is also finite, then order of X must divide order of G. Okay. So, this is something we will prove later, but now from this it is clear that if you have some element in G such that order of that element is D, then D must divide n. So, this equality makes sense. Okay. So, because we want to restrict D only for the divisors of capital N. So, now given X, it must be in one of this AD, but if I fix this AD, okay, suppose AD is non-empty. So, that means there exists some Y in AD, but order of this Y is D. So, now if you take this subgroup generated by Y, the cardinality of this must be D. But what our hypothesis says? Our hypothesis says there exists at most one subgroup of order G. So that means this AD must be contained in this subgroup generated by Y, because if I start with any other element Y dash in AD, that also will have order D, and then if you look at this subgroup generated by Y dash, that also that must be same as the subgroup generated by Y, because there exists at most one subgroup. So that forces that this AD is subset of the subgroup generated by Y. But how many elements are there of order D inside this cyclic group generated by Y? There are exactly phi of D elements. Okay? So that tells us that the cardinality of AD is exactly phi of D if AD is non-empty. Okay? So that tells you that from this equality, okay, call it star. So from star you get the cardinality of G, which is capital N, is exactly equal to summation the cardinality of AD D divides N. But this AD, the cardinality is exactly phi of D if AD is non-empty. So this is less than or equal to, because some of the AD could be empty, we do not know. Okay? So this is exactly equal to summation phi of D divides by N. But note that this is exactly equal to N. That is what we already observed by applying our analysis for the group Z modulo NZ. So if we take Z modulo NZ, using our understanding, we proved that N is equal to summation phi D divided by N. So that means here you have N less than or equal to, equal to this, which is less than or equal to N. Since equality of this left hand side is same as right hand side, that forces that the equality happens in the middle as well. So that means, so this summation D divides N mod AD should be exactly equal to summation phi of D divides N. Since all of them are non-negative integers, so that forces, they are actually positive integers, that forces that the cardinality of AD must be equal to phi D for all D divides N. In particularly, you can take D equal to N, that forces that the cardinality of AN is exactly phi N. Okay, that means AN is non-empty, because phi N is at least 1. Okay. So now we have proved that AN is non-empty, but that is what we wanted to prove. AN is non-empty implies G is cyclic. So that means if G is a finite group, has the property that given any divisor D of the order of G, there exists at most one subgroup of order G of order D. So then that G must be cyclic. Okay, it's a very, very important consequence. So let me stop with one important corollary. So if you know what is a field, okay, if F is a field, so then if you take the multiplicity group, those are all non-zero elements in X in F. Okay, so that will form a group. For example, C star you can take. So any finite subgroup of this field, so multiplicity group F cross must be cyclic. So any finite subgroup G must be cyclic. For example, you can take F to be complex numbers, okay, and any finite subgroup of C cross must be cyclic. That is what we have proved. Why it is the case? You take the cardinality of G to be capital N, okay, then again you have to use Lagrange's theorem. Okay, if D divides N, okay, then if you look at the subgroup of order D, okay, suppose H is a subgroup of G of order D, then you can prove that this H must be those X inside F cross. Okay. So, maybe I will put it like this way, those x in G such that x power d equal to 1. Okay. And for x power d equal to 1, there are only exactly d solutions in a, at most d solution in a field. Okay. So, that means, so it that H has only that d roots of unity, okay, at most. So, that means either H exists or H is exactly equal to those x in F cross such that x power d equal to 1. So, that means it is the group either exists or it is the unique group given by this. Okay. So, this again uses Lagrange's theorem. Maybe after introducing the Lagrange's theorem, I will come back to this. We will come back to this. Okay, I will stop here. So, we will continue next class with the homomorphisms and some basic properties of homomorphism.